y equals x squared.
Minus x.
Minus x, thank you. Stop reading too quickly. Y equals x cubed minus 4x squared plus 3x. And we're asked to graph those on a common screen and observe that the region between them consists of two parts. Find the area of this region. Okay, so this is your question. And what were your thoughts when you initially started?
Well, when I did two different ways, and I got because initially, I graphed them out, and so I had one little chunk in front of it had one graph on top of the other one, so I put that as one unit.
Okay.
And then they kind of flip-flopped their positions on the other half of it,
Okay.
and then they added in that and switched the equations as to which one was on top and which one was on bottom.
Okay, so why don't we go ahead and take a look at what these functions look like. So we've got x squared minus x, and we've got x cubed minus 4x squared plus 3x. And so I'm going to start with a zoom standard and just kind of see what happens here. All right, and so when we first graph this, and it's nice that the textbook question gives us this hint that there are two separate regions, because this one little itty-bitty region in here is kind of tough to see at first, but there are two separate regions, so I'm going to go ahead and zoom in and change my window a little bit. Maybe the best thing to do, well, I'll just go ahead and change the window. It looks like we have x values, certainly not less than -1 and not much greater than +5, so let's change those. And the y values, maybe we'll look at -5 and 15. Oh, and it's sad that we really kind of lost part of that function in there, so let's change windows one more time. Okay, so that's pretty close to what it looks like. All right, so I'm going to go ahead and draw this picture over here. And I might exaggerate a little bit of what's going on here. We've got the parabola, which dips down below the x-axis and then pops back up. And this is the graph of y is equal to x squared minus x. If I wasn't sure, I could just be very careful about which one I type in first, but the parabola is going to be the square, the quadratic function. And then our cubic one, the one that goes up, down, and then back up again, that'll be the x to the third function. Okay, so it looks like we have something that looks like this. And then these guys kind of cross somewhere up there as well. Okay, now this is our function y is equal to x cubed minus 4x squared plus 3x. Okay, so the regions that we're looking at here are this little itty-bitty bubble as well as this much larger, I don't know what shape this is, some other shape over here. Okay, any questions about the picture? Okay, so some other important pieces of information are going to be to figure out these intersection points that we have. And so I can do this a couple of ways. One way is that I can set the two functions equal to each other and solve for x. And so maybe I'll try that. And so we've got x squared minus x is equal to x cubed minus 4x squared plus 3x. I have lots of x's raised to lots of power, so I want to move everything to one side. And so we've got x cubed minus 5x squared plus 4x is all equal to 0. And so now the question is, can I factor this thing? And the answer is absolutely. I can pull out an x. And I'm left with x squared minus 5x plus 4. And then the next question becomes, can I factor this leftover term here?
X minus 4x minus 1.
So if we factor, we can get x minus 4 times x minus 1. You can double check that that works. And so we end up with 3 roots. And so I know that either x is equal to 0, x is equal to 4, or x is equal to 1, which it makes sense from the picture as well. So here's our x equals 0, here is x equals 1, and this last intersection point is over here at x equals 4.
Oh, sorry. It's 4x minus plus 3x, so when to change to 4x?
So when I added this minus
Oh,
section
yeah.
here, I added it over to the other side.
Gotcha.
Okay, other questions? Okay, so before we do any sort of calculus, the number one thing we want to do is understand what the picture looks like. Okay? If we don't have an understanding of what the picture looks like, then setting up the integral is nearly impossible. Okay, so let's again, if you prefer not to do the algebra of setting the two functions equal to each other, you can also use your graphing calculator and find the intersection points from that. Okay, so we have our picture, and Jody, you were right to observe that part of this function, or part of this graph, one of the functions is on top, and the other part, the other one's on top. So if I go ahead and draw these in different colors, that's helpful, I think, to be able to see what's going on there.
It's just inverse. And the inverse.
All right, so because we have these two separate regions, we have to set this up into two separate integrals, and so our total area is going to be, for the first region, when I look at this part, I want to think about having a vertical rectangle anywhere in that region. There it is. And the area of that standard rectangle, notice that anywhere within this interval from 0 to 1, whether I slide that rectangle, imagine it sliding to the left or to the right, no matter what, the top is always on the blue function, the bottom is always on the red function. Anytime that you set up an integral like this, you want to imagine sliding that rectangle back and forth and making sure that the essence of the rectangle, where it actually resides, doesn't change its characteristic anywhere within that interval that we're looking at. So this is a good standard rectangle. Our top is the blue function, and so we've got
X cubed minus 4x squared.
our blue one, x cubed minus 4x squared plus 3x minus the bottom function, which in this case is the pink one, which is x squared minus x.
Nice.
And so this is the height of our rectangle. The width of our rectangle is a little bit in the x direction, so that's dx. And then we want to add up all those rectangles starting at x equals 0 and ending at x equals 1. So that's our first region here. We now need to add on the second region. Are there any questions about the first region? Okay, so now to continue on, our second integral is going to be top minus bottom in our new picture in the second region here. Our rectangle if I draw a standard rectangle kind of somewhere in the middle, and I imagine sliding it to the left and sliding it to the right, even if I draw the little rectangle up here, my rectangle is supposed to be parallel to the y-axis. Even up here, the top is on the pink and the bottom is on the red. Okay, so anywhere in this region over here, from 1 all the way over to 4, we're looking at top pink minus bottom blue. All right, so our height looks like the pink one, which is x cubed minus x, minus the blue one, which is x cubed minus 4x squared plus 3x.
X squared minus x.
Yeah, thank you. X squared minus x. So we've got top minus bottom. So that's our height of this rectangle. The width is a little bit in the x direction, so that's dx. And then we will add up all those rectangles, starting at an x value of 1, and add until our very last one ends at x equals 4. So integral from 1 up to 4. Okay, so now we've completely set up an integral to describe the area of these two shaded regions. Are there any questions about that? Mike?
So
which is your top value and which is your bottom value?
In terms of up here, for example?
Yeah.
So when I look at this one, this is my top, and this is my bottom. So whenever I want to find the height of a rectangle, I'm going to take that top number and subtract off the bottom number, or in this case, the top function and subtract off the bottom function. So when I'm looking over in this part of the picture, the top of that rectangle is touching that blue function, which happens to be labeled as this guy. And then the bottom one is the big one, which is labeled as this guy. Other questions or comments? Okay. So if I want to continue and actually evaluate these integrals, the very first thing I would want to do once this is all set up is to simplify the integrands, which 99% of the time is going to involve distributing a negative sign and then combining some terms. And so my next step, this step right up here is my setup but do not solve kind of step. And if I then want to solve, I have the integral from 0 to 1, and I've got an x cubed minus 5x squared, and then plus 4x. And then I'm going to add that on to the integral from 1 to 4. And what you'll notice is that I'm going to get the exact same answers, but they're going to have negative signs in front of them. And so I've got negative x cubed minus, I'm sorry, plus, let's see, so we've got negative, I've got x squared plus 4x squared and plus 5x squared, and then minus 4x. And so now these are my two integrals that I'm working with, and I need to integrate and plug in the boundaries. Joan, does that answer your question?
I got that far, but I still got
So you got to that point so far?
Mm-hmm.
Okay, so let's go ahead and crunch the numbers and see what's happening here.
I got 407 divided by 6.
407 divided by 6.
I don't know if it's right though, because
So let's see what happens. Okay, so now I want to integrate, so I can add 1 to the power, x to the 4th over 4, minus 5/3 x cubed, plus, add 1 to the power, when I divide by the new power, I've got 2x squared. And I'm going to evaluate this whole thing between 0 and 1. And so I'm going to go ahead and work on this entire first integral here, and then we'll come back and work on the second one. And so the first thing we'll do is plug in 1, and so we've got 1/4 minus 5/3 plus 2, and then once I plug in 0, everything here turns into 0, and so I just have a minus 0. Okay, so I'm going to go ahead and leave those fractions there, and we'll combine them with the other terms in a little bit. Our second integral over here, we've got x to the 4th over 4, and I have a negative sign in front of that, plus 5/3 x to the 3rd, minus 2x squared, and we're going to evaluate between 1 and 4. Okay, so first things first, I'll plug in 4. And so we've got negative 4 to the 4th over 4, plus 5/3 times 4 to the 3rd, minus 2 times 4 squared. And all that we are going to subtract off, and this guy is definitely all that we're going to subtract off plugging in the 1. And so we've got negative 1 to the 4th over 4 plus 5/3 times 1 cubed minus 2 times 1 squared. All right, any questions or comments about this so far? Okay, so this first part is not too bad. The quarter minus 5/3 plus 2. And then we've got negative 4 to the 4th. One thing to be careful of here is that this negative is not being raised to the 4th. There's not parentheses around that. And so this does in the end become, anybody know what 4 to the 4th is? 64. So 4 to the 4th is 256 divided by 4 is going to give you 64. Okay? So we've got negative 64. We've got 64 times 5 over 3. What is 64 times 5? 320. Okay, so we've got a plus 320 over 3. And then we've got minus 32. And now this last part here, I'm going to go ahead and write this as minus, and then inside parentheses we've got negative 1/4 plus 5/3 minus 2. Alright, so this is a lot of number crunching here in the end. So working out these numbers, I've still got a quarter minus 5/3. 2 minus 64 is minus 62 plus 320 over 3 minus 32 plus a quarter minus 5/3 plus 2. And I'm a little bit sad because I was really hoping the quarter would cancel this quarter and I wouldn't have to worry about them, but they don't. They get added together. So, alright, so what do we have here? We've got 2 quarters. We've got minus 10/3. Oh, and plus 320, so that is plus 310/3. And then, somebody help me with these whole numbers here.
90. Minus 90. Minus 92. Minus 92.
Do I have a second on that number?
Second.
Great. So negative 94 and then plus 2 at the end. Alright, so we're getting closer. This one here we can reduce to a half, so let's write that as a half. And then we need a common denominator if we're going to finish this out. So we've got 3/6 plus 620 over 6 minus, what's 92 times 6?
552.
552. Do I have a second on that number?
Yes.
Great, 552 over 6. Okay, we're almost done. We almost have all the arithmetic done. So, somebody help me with 3 plus 620 minus 552.
140. It's going to be 71 over 6.
71. 71? Do I have a second on the 71?
Second.
Second, third. Final answer of 71 over 6. Is that one of the answers you got?
No, I found my problem. For some reason I ended up with 320 over 81. I don't know why, but
Yeah, I found my problem too.
Heck yeah. Yeah, that's going to totally mess everything up.
I got everything right though to that point.
So what are the important things to focus on in this problem? The important things to focus on in this problem are, number one, do we know what the picture looks like? And can we analyze the picture in order to set up this integral or integrals, which describe the area between the two curves? So setting up the integral is number one most important. Okay? And in order to be able to set up the integral, it's very helpful to have a picture. Second most important thing after the integral is set up, and setting up the integral is like way up here. And then after that, evaluating these integrals is kind of down here. Okay? So finding the antiderivatives and plugging in those values. And then this last part, this part where we're number crunching a bunch of fractions and things like that, it's useful if we can get to a final answer, but in terms of calculus, the important part is done right here. Unfortunately, this last part is the part.
How would you
where
look at that on a test then?
How would I look at this on a test? I would probably look at it and say, first of all, on a test, I may ask you to set up but do not solve, in which case you would stop right here. And if I ask you to set up and evaluate, then I would look at your first 2 lines, and then I would not work with all of this. I would say, okay, here's this step. Did they crunch the numbers and get the final answer for the final point on the exam? So that's how that would work.
So you would
But-
just miss 1 point on that problem if you didn't get the final answer right.
Yeah, something like that, yeah.
So you made some mistakes in signs and,
Right.
right.
Right, and I don't want to, there are 38 of you in this class, I do not want to pick apart whether you forgot your negative sign right here
Right.
or put an 81 in the denominator up here, or something like that,
Right.
so, yeah. All right, other questions about this problem right here? Okay, so some of you may be wondering, and I neglected to say this at the beginning of the class, so great, volumes. And technically, the full name is volumes of revolutions. Okay, so we are going to start today with an example. So consider the area bounded by the equations y is equal to x squared minus 1/4 x cubed, x is equal to 3, and y is equal to 0. Okay, so if you have your calculator, please go ahead and pull it out and graph the function y equals x squared minus 1/4 x cubed. One thing you'll notice is that we're stopping at x is equal to 3, so in terms of your window, you can change your window so that the x maximum value is x equals 3. Okay, so once you get a picture, turn to your neighbor and share your picture with your neighbor and see if they agree. Alright, so hopefully your picture looks something like this. The function kind of dips down, touches the x-axis, and then bounces back up, kind of flattens off, and then drops down. And approximately just slightly past the top of the hill is where x equal to 3 is located. And so what we are looking at here is an area that is bounded by y equals 0, that's the x-axis, x equals 3, that's a vertical line, and then this curve, which is y is equal to x squared minus 1/4 x cubed. So we are looking at this region right here. Okay. So at this point, based on section 7.1, I might ask you to find the area of this region, and we could draw a rectangle in there and have the top of the rectangle on this function y equals x squared minus 1/4 x cubed, and the bottom would be on 0, and so our bottom would be minus 0. Okay? And that would be fine, but what we're going to do today is a little bit different. So what we're going to do is we're going to take this picture, this region right here, and we are going to fix the x-axis. We're going to take this picture and we're going to rotate it out of the board, swing it down, have it rotate through the back of the board, and come back up to where it started. So sort of like one of those poofy paper party decorations where it starts out flat and you open it up and it makes like a bell or something like that. That's essentially what we're doing here. So I'd like you to try and imagine in your head what this object will look like when we take this flat spot. Don't say anything out loud yet, but when you take this flat spot, swing it around, bring it back up through the board. All right, now I'd like you to describe that object to the person sitting next to you. What does that look like?
Kiss?
Like a top?
You
Spinning
know
top?
those chocolate kisses?
Yeah. Kids or a spinning top.
On its side?
All right. Does anybody have a neighbor who had a good description of what this object would look like. This, once we have taken this and rotated it around the x-axis.
Chocolate kiss on its side.
Chocolate kiss on its side. Anybody agree with that? Anybody have something different that they thought it looked like?
A beat, kind of like a beat turned on its, or with the top cut off.
Like a what?
A beat.
Oh, a beat.
Yes.
Okay. All right, a beat with its top cut off. Okay. That seems reasonable. Any other suggestions?
Wine glass?
I'm sticking with my wine glass idea. Here it is.
So the stem would then be down here. Okay, so the wine glass works as long as you filled it with something. So it's got to be a solid wine glass. Perfect. So wine glass full of wine.
Perfect.
Okay, and the stem cut off. Okay, other suggestions.
Full up to x equals 3.
Right, full up to x equal to 3, and then we'll stop the wine glass after that. Okay, other suggestions? All right. Well, unfortunately, I did not bring along any beets, and I don't think I'm allowed to bring wine glasses with wine in them. But I did bring some Hershey Kisses so that we can analyze this solid as a whole. So the question becomes, once we take one of these pictures and we rotate it around the x-axis, I'm totally leaving this up to you to open that. So I'll pass these out. Before you eat it, I want you to analyze the shape of the Hershey Kiss. And the question becomes, what is the volume of our solid that we get when we rotate the region about the x-axis. And so our solid shape looks like a Hershey Kiss, but the problem is that if you look in the front of your textbook, I don't think that there's a formula for the volume of a Hershey Kiss there. And so in that case, we're going to need to work on coming up with the volume of a Hershey Kiss.
It goes back.
Don't think that means anything.
Did you stop the y-axis just for
Right here. So what I did is normally see this function would continue up in this direction, and because the x squared minus 1/4 x cubed touches right here at the x-axis at the origin here, then this is in fact the region that is bounded by y equals 0, x equals 3, and this curve. If I come over here, this is unbounded. Okay, did everybody get at least one Hershey Kiss? Okay, so take a look at your Hershey Kiss, turn it on its side, and once you've done that, imagine what the volume of that Hershey Kiss is. All right, so as you're looking at that, also imagine what it would look like to draw the picture of this Hershey Kiss as it's rotated around the x-axis. Okay, so I've taken this curve, and I've just taken the portion of it that I care about, the portion that has to do with the colored area here. And I want to rotate around the x-axis, so it's going to come out of the board, it's going to pop back, and it's going to make a mirror image on the other side of the x-axis. And right now this is a flat picture, but I actually want to imagine, rotating this thing around. So I'm going to get rid of this vertical line here, and instead give this guy some circularity here. All right, so what I've got here, it almost looks like a beet with the top cut off, but maybe more pleasantly a Hershey Kiss. And so here this is popping around. The base of the Hershey Kiss is occurring at x is equal to 3. Okay? And the tip is occurring here at the origin.
Pi r squared times the Riemann
yeah, we don't know the area of a Hershey Kiss, but if we do slice it, like Mark is suggesting, imagine taking this thing and slicing perpendicular to the x-axis. It's going to create a bunch of little discs, almost like little coins stacked on top of each other. Up here we'll have very small, tiny coins, and the base will be a very large coin. And so, actually this is a really good idea. So I'm going to draw one of these coins on here. So here is one typical slice of our Hershey Kiss. Alright, so imagine taking your Hershey Kiss and a very sharp knife, turning it on its side, and going slice, 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 slice. Okay? And you get a whole bunch of slices. If I take one of those slices, and I'm going to turn it and put it on the side, it looks something like this. This is a blown up version of one slice. And it's got a radius, which I might call R. And notice that all those slices are exactly the same, except for their size. We've got little itty-bitty coin-shaped slices over here. We call them discs. We have larger ones down here on the end. But no matter what, no matter which slice we look at, the radius of that slice, that radius there depends on the function that we're looking at. And so if I describe a generic volume of this disc right here, the volume of one disc, well, it's essentially a really flat cylinder, right? And a cylinder has volume pi r squared times the height. Where our height is this little width on our disc. The radius is from the center out to the edge. And then the pi is just pi, which, by the way, Pi Day is coming up, March 14th. Start thinking about how you want to celebrate. Okay, so the volume of one disc, if I look back at my picture right here, then what we're going to do is to find the volume of our solid Hershey Kiss. We'll slice the solid into discs. Each disc has a volume equal to pi r squared times the height of the disc. And the idea is that we'll calculate the volume of each of those discs, just like a Riemann sum, calculate each individual volume, and then we'll add them all up. We'll find the volume of each disc then add all those volumes to get our total volume of the solid. Alright, so in terms of the integration or the Riemann sums, what we're doing is we're saying that total volume is equal to pi r squared times the height of our disk, all added up. Okay, so let's take a look at our example. In our example, we have one standard disk right here in the middle, and so the volume of that disk is going to be pi r squared times our height. And the height of a disk is, it's almost so small, I don't want to call it a height, I might call it a thickness. Pi r squared times the height, or pi r squared times the thickness. And so the volume of one disk is pi pi r squared times our height or times our thickness. Our height of this disk, the thickness of this disk, that's just a little bit of change in x, a little bit of width in x, and so that is going to be dx. So the thickness of our disk, or the height of our disk, is dx. And the radius of our disk, well, whether I look at this disk very close to the very tip of your Hershey Kiss, or whether we look at the disk that's way down here at the base, no matter what, that height, that radius right there depends on that curve that's along the edge. And so our height, or I don't mean our height, our radius is going to start at 0 and go up to our function. And so in this case, our radius will be our function itself, which is, I lost it. What was the name of it? Think of it. X squared minus 1/4 x to the third. So I'll draw that up here. That is this guy right here. Y equals x squared minus 1/4 x to the third. All right, are there any questions about identifying the height or the thickness of our disk and the radius of our disk?
Would the radius be squared too? All
That's
that
right. So
squared?
this is just r, and then we're going to actually square it.
Okay.
Yes.
And then wouldn't you indirectly think of the height as dr, sort of, kind of?
This height here, what you want to be careful, r is actually this length here, and the height or the thickness is perpendicular to r, and so it really is a different variable for us. And so, and in this case, that distance is a little bit in the direction of the x-axis. Eventually, we're going to see disks that we're going to be slicing the opposite direction, in which case we'll have a dy.
Yeah.
But yeah, it is perpendicular to r. Okay, so the volume of our disk, once I have all these pieces, is going to look like pi times r, which is x squared minus 1/4 x cubed, pi r squared, times dx. Okay, so things are looking good because notice that the thickness here is dx, and the variables that I have inside here that have to do with my radius are also x values, so that's good. I need for my variables to match up. And so now our total volume is going to be the volume of one disk, a symbolic disk, which is pi times x squared minus 1/4 x cubed, the whole thing squared, dx. And we will do that for every single slice of this Hershey Kiss, starting with the little itty-bittiest one at x equals 0. So we're going to add up all those volumes starting at x equal to 0. And we slice and slice and slice and slice and slice and slice and slice until we hit the base of our Hershey Kiss, which occurs at x equal to 3. And so now we have an integral which describes the volume of our Hershey Kiss. Are there any questions about writing down an integral? So this is our first example of using an integral to talk about something other than areas below a curve or between two curves. And the idea is that we're taking this solid object and we're slicing it into pieces where each piece is essentially the same shape, in this case the shape of a disk. And we know what the volume of a disk is. And so when I look at that, which is pi r squared times the height or times the thickness, then I say, okay, I can come up with a formula for the volume of a typical slice, and then add all those up. And that's my Riemann sum, which when we take a limit turns into an integral. Right, any questions about this idea? All right, so our next job is to actually crunch out the numbers and figure out what the volume of our Hershey Kiss really is. So we've set up the integral here. We now need to solve this. A few things we can do to make our lives easier is we can pull that pi out into the front. And in addition to that, I look at my integrand and I think, oh, I've got fancy stuff raised to a power. And so can I use a u substitution? No, because if I let u be my inside function, the derivative's not going to get canceled. So my best option is probably going to be to expand this out. Alright, so I'm going to expand the x squared minus 1/4 x cubed. And remember, when we expand, we actually have to distribute stuff. And I don't mean distribute by just putting the square inside here. I need to make sure that I multiply everything out. Okay, so I've got x squared times x squared is x to the 4th minus 1/4 x to the 5th minus another quarter x to the 5th plus 1/16 x to the 6th. Now I can combine some like terms, and we've got x to the 4th minus a half x to the 5th plus 1/16 x to the 6th. And so this is work I might be doing off to the side, and once I do that, then I can write down my volume and say that my total volume, which was equal to the integral from 0 to 3 of pi times x squared minus 1/4 x cubed, quantity squared dx, is equal to, I'm going to pull the pi out in front, so I have pi times the integral from 0 to 3. We've expanded out the parentheses, and so we've got x cubed minus 1/2 x to the 5th,
X to the 4th.
4th,
Oh, first one.
for the first one, yeah. I'm glad you're here, Dennis, thank you. X to the 4th minus 1/2 x to the 5th plus 1/16 x to the 6th. And then we still have our dx. Okay, are there any questions about anything we've done here so far? So the new stuff was setting up this integral. Once we've set it up, then we go back to our techniques of integration. So at this point, now that we've multiplied out, now we've expanded our stuff squared, now it's a matter of using the power rule. And so I've got this pi out in front, and then we have x to the 5th over 5 minus 1/2 x to the 6th over 6 plus 1/16 x to the 7th over 7. And we're evaluating this between 0 and 3. Alright, so we've got our pi, we've got 3 to the 5th over 5, minus 3 to the 6th over 12, plus 3 to the 7th over 104? Okay, oh, all over 104.
112.
100, how did I get 104 and 112? And then we're going to take all that and subtract off, plugging in 0, which every single one of these will end up getting 0. I do want to caution you, don't get too lazy about that, because it's only when you have polynomials that when you plug in 0, you get 0, but when you have sine functions, cosine functions, exponential functions, the 0 actually does stuff. Okay, so now we've got this number. Now, in the end, since we want to know how much chocolate we're eating, then I don't really care about an exact fractional amount with a pi involved, and so I might come up with a decimal approximation. So if you have your calculator, please crunch out these numbers, multiply in the pi, and come up with a decimal number that is maybe good to 2 decimal places. When you get a number, check with your neighbor. 23.17? Okay. 23.17. Now, I never gave you any measurements for our original Hershey kits, and so I don't know whether this is inches or centimeters or feet, probably not feet. But in the end, we're talking about a volume, and volume is measured in cubic units. And so this is 23.17 cubic units. All right. Are there any questions about that? Okay. Then let's stop here. Please take your 10-minute break. Please help yourself precursor to Calc 3, and I hope all of you are going to be eventually taking Calc 3. And by the way, we just finished our schedules, and I will be teaching a section of Calc 3 in the fall. So I think it's 12 to 2, but I forget which day, if Monday, Wednesday, Tuesday, Thursday. So I'll get back to you on that on Wednesday. It is one of the days that ends in Y, yes. Yes. Okay, so let's take a look at a second example. Okay, so we'd like to find the volume of the solid generated by rotating the area about the x-axis, by rotating, I should say, the region about the x-axis. Now, what region am I talking about? Well, the region is bounded by y equals x squared, y equals 4, and x is equal to 0, and we're only talking in the first quadrant. Okay, so there's a lot of description going on here. We're talking about finding the volume of a solid, and so that means that we are going to be starting with some flat two-dimensional picture and then rotating around the x-axis. So the first thing we want to do is to identify what this flat two-dimensional picture looks like. And so this was not too hard. I can do this with my calculator, but I already know what y equals x squared looks like. I also know that we're only looking in the first quadrant. So here is y equals x squared. Again, I don't really care about the second quadrant over here. I just drew it for completeness. And so we've got y equals x squared. We have y is equal to 4. And we have x is equal to 0. Okay, so I'm starting out by drawing all these pictures, and then I go back and I say in the first quadrant. So in order to make my life a little bit less confusing, I'm going to go ahead and erase this stuff over here in the other quadrants, just so that I don't accidentally start coloring things in. And so the region I'm looking at is region bounded by y equals x squared, y equals 4, and x equals 0. So we are looking at this region right here.
A little bit greater than 2/3.
What's that?
A little bit greater than 2/3.
So it looks like, you mean in terms of if I were to kind of draw this region here, like that?
Yeah, like if we're going to do the swing around, right?
Okay.
And that's going to basically make a shape that has a bit like a...
Just hold off on that thought for a second. And then give everyone a chance to think about what it's going to look like before you say it out loud. Okay. So we've got this region. Here it is. We're going to take this region, we're going to swing it around the x-axis. And I think that this step is really important to imagine in your head and really visualize, okay, what will this solid look like when we take this region, swing it about the x-axis, bring it back through the board, and bring it back up. So imagine what that looks like. Mark started to describe it, and I cut him off. I'd like you to describe it to your neighbor. What does this solid look like? How would you describe this to somebody who just walked into class?
Circular disc. with the thing going down in the center. Go like a hockey puck. But in the center, it would be going down.
Kind of like
It kind of reminds me of just what we were doing before, but just all that now is the area instead of the Hershey Kiss, you know what I mean? It's just the other area now.
yeah.
Right, you could say the Hershey Kiss is going into a hockey puck.
I'm confused.
The difference between taking it or the volume of doing that and the volume of seeing this rotating about the wide axis.
Okay, that's a good question, we're gonna address that.
Right.
Okay, anybody have a good description of what this looks like?
Maybe 2 years?
2 years? Okay, so when I bring this out and I swing it back in, then the flat picture is going to look something like sort of this guy up here, and then we'll also have one down below.
It's kind of just like the Hershey Kiss, but just everything else is now the area instead of inside the...
It's like a hockey puck with the Hershey Kiss taken out of the center.
Package.
All right, so this isn't quite an accurate drawing, what I have here. If I imagine this solid, around the outside, we actually have a flat cylinder around the outside, and that Hershey Kiss is being taken out of the middle. Okay? And so this part is hollow, and so maybe a better drawing of what I might do is, I might start by saying, okay, here is,
Jello mold.
what's that?
He said
Keep
funnel
going.
cake, I think, earlier, and yeah, Jello mold, like you see these.
No, the hockey puck.
Of course, it's the external, kind of like the wine glass analogy was, but yeah, it was
It's the
full.
American if you didn't.
Yeah, so if this thing were, yeah, we can kind of think of it that way as well. So my outside part looks like, let's get this nice. My outside is this cylinder. And then inside, here we go, here is our axis. My inside is carved out, hollowed out, this almost like we pulled that Hershey Kiss out of the middle. And so this portion inside here is hollow, and this part here and around, this base part, is very solid. So if we were to turn it on its side and try and fill it with water, then it's possible that there might be just a itty bitty little drop that would come out of the middle down here on the bottom, or it might have sealed itself shut. But so we have very little water. If we were to fill this hollow part on the inside, it would grow wider toward the top. Okay, so this is our object. All right, are there any questions about our solid? What you want to practice as part of your practice problems is being able to draw the region, and then imagine that region being rotated around the x-axis or whichever axis we're talking about, and then sketching a picture of the three-dimensional object. You want to be able to have a working diagram and a description of what the solid looks like as well. Will I be grading you on your artwork? No, absolutely not. But if you feel like your artwork is insufficient, then add some words to describe what you're trying to draw. Okay, so this is our solid. Now, we'll ask the question during, when everyone was chatting, you said, well, what if we took this picture and rotated around the y-axis instead? And you can imagine that your picture is going to be very different, and your solid will be very different. And later on, I'm going to ask you to look at some different options of rotating around maybe the x-axis versus the y-axis. And you'll figure out whether, will this give us a different volume? Will it be the same volume? Is it a different shape with the same volume? Lots of different questions to ask about that. Okay, so here's our solid. Now, what we want to do with this is we want to take our solid and we want to slice it perpendicular to the axis of rotation. And so when we slice, 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 slice. A typical slice is going to be round on the outside. But it's also going to have a hole out of the middle. All right, so a top-down view of this slice is that we have an outside part, and then we have our inside part that's the hole. And then this is the solid part in here. Yes?
Would it be easier when you want that, just take the cylinder
Mhm.
and subtract the shape of the sheet face, so the area of that?
So absolutely. So an alternate way of thinking of this is saying, okay, we've got our outside cylinder. Let's find the volume of that cylinder, and then subtract off the volume of the part that we're taking away. So that would be an alternate way of thinking about this. And similar to the areas, what my overarching theme of this whole chapter is take whatever solid we have and break it into pieces that are very similar to each other. Find the volume or the area of that piece, and then add them all back up. So that's why I'm going about it this way, but that's option B. Absolutely, and it works just as well. Okay, so in this case, my standard object that I'm looking at, my standard slice, is a shape which looks like a washer. So it looks like a disc with a hole drilled out. And we'll call that shape a washer. And so if I want to think about the volume of one of these washers, the volume of one washer is going to be the volume of the large washer. So maybe I'll call this large one a radius of big R, and the radius of the small hole I'll call a radius of little r. So the volume of my big washer is going to be pi times big R squared. Now, remember, there's a little bit of thickness to these things, so I can add onto my picture a little thickness, both on the inside and the outside hole. So the volume is pi r squared times that thickness minus the volume of the part that's drilled out. So minus pi times little r squared times the thickness or the height. Alright, so here's the volume of one of these washers. A nicer way to write this might be pi times big R squared minus little r squared times the thickness. And so then if we want to come up with the volume of the entire solid, then our total volume, is going to be the volume of one washer, which is pi times big R squared minus little r squared. Add up all those volumes starting at A and ending at B, whatever A and B are. Okay, so let's look at our particular example. So in our example, we want the volume of one of these washers. Okay, are there any questions so far on kind of like the idea that's going on here? When I imagine slicing, one typical slice looks like a disc but with a hole cut out of it. And the volume of one of those slices is pi times our big R squared minus our little r squared times the height or the thickness of that washer. Okay, so in our example, things that we need to know the thickness of our washer. And so when I look at that, that's a little bit of thickness, and it's in the x direction. And so our thickness is going to be dx. And the other two pieces of information we need to know are the large radius and the small radius. So when I draw this picture, my large radius is the radius of the blue ring. And so that goes from the x-axis out to this straight line across the top. And no matter whether I slice all the way on the left or all the way on the right, what is that large radius? Yeah, it's 4, because if I imagine over here on my two-dimensional drawing, that is a height of 4, so it goes from the x-axis up to 4. And so our large radius is 4. Now the inside radius, that pink one right in here, when I look at that one actually changes as we move along, but no matter what, whether I'm looking at a slice all the way to the left, all the way to the right, or anywhere in the middle, that radius starts at the origin, at the x-axis, and goes up to our curve. In this case, our curve is y equals x squared. And so our little radius, little r, is x squared. Right, are there any questions about any of that information? Okay, so now let's put all this information together. Our total volume is going to be pi times our big R squared, so that's 4 squared, minus our little r squared, so that's x squared quantity squared, times our thickness, which is dx, and we're going to add up all of those washers, and in our picture, our washers are starting at an x value of 0, add, slice, 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 until we hit the end of our solid. Now, where did that occur? Well, that occurs at whatever x value this is. Okay, Joe, you say 2, why do you say 2? How do you know that?
Where is that on that one?
Right here?
2 squared is 4.
Yeah, great. So we're looking at the intersection of these two curves right here. We've got intersection of y equals 4 and y equals x squared. So 4 equals x squared. X must be equal to plus or minus 2, but since we're talking about our first quadrant, x is equal to 2. Great, so that's our x value, that's our top number, so we go from 0 up to 2. Alright, so we've now set up an integral which describes the total volume of our solid. Are there any questions about setting that up? Okay, our next step would be to solve this integral. And if we wanted to solve this integral, then what we would need to do is to first do some simplifying, pull that pi out in front. And so we'd have pi times the integral from 0 to 2. And I might clean up inside the parentheses. And so we've got 16 minus x to the 4th, and then we've got a dx at the end. And now I can do my antiderivative. And so there's some work in between, but you might check that as a final answer, an exact final answer would be 128 over 5 pi cubic units. And you should check that. Okay, are there any questions about that one? Very much. Going twice? Yes?
If you were to do it with respect to y and do it around the y-axis, would that get you the same?
So that's a really good question. So let's see what happens. So if we take this same picture, and we start out with the same region, so same region, so we've got y equals x squared, x is equal to, what did we say it was?
0.
X equals 0, y equals 4 in the first quadrant. And instead, we now rotate about the y-axis. All right, so now we'd like to find the volume of this new solid. So I'd start out very similar, exactly the same, in fact, as I did before. I'd start by drawing my picture of the two-dimensional region, and so here's y equals x squared, and then I've got y equals 4, and the region that I'm looking at is still exactly the same region here, and I know that this x value is 2 from our last example. And now I want to rotate this about the y-axis. So this is going to be a very different looking solid. In fact, what's going to happen is the top of it's going to be totally flat. And we're going to take this picture, it's going to rotate around, pop in the other side of the board, and swing around the back. It's almost going to be like a bowl, but not an empty bowl. It's going to be a bowl filled with cement. So the object that we're looking at is going to, let's see if I try and draw this. So here is a picture of my solid. We'd like to find the volume of this solid. Now, in this case, when I slice, because we're rotating around the y-axis, my slices are going to be perpendicular to the y-axis. And so a standard slice is going to be somewhere in the middle here. It'll have a little pike to it. And in this case, our standard slice does not have a hole in the middle. So our standard slice in this picture is going to be a disc rather than a washer. So my slice is a disc, and the volume of one disc is pi r squared times the height or times the thickness of that disc. All right, now there's a few things that I need to deal with here. This is our first example where we're rotating around the y-axis. So notice when I created my slices that now my slice, which is perpendicular to the y-axis, that thickness right there is a little bit in the y direction. And so that means that my thickness is going to be dy. Now something that you might have noticed when you worked on the areas between curves homework is that when you had horizontal rectangles instead of vertical rectangles, you had to change a lot of things about your functions. In particular, the part that goes in the integrand next to the dy must be in terms of y's rather than in terms of x's. And so when I talk about this radius here, my r is going to be, well, whatever this curve is here. So my radius is going to be the formula for my curve, but it must be a formula that's in terms of y's rather than in terms of x's. So I can't write down r equals x squared because then that won't match with my variable dy. So what I need to do is to solve this equation for x. All right, so I've got y equals x squared, and so that tells me that x is going to be equal to plus or minus the square root of y. Now, in this case, my region, this is the positive square root of y. The negative is on the left-hand side. Our original curve is the positive value, so that's the one we're going to choose. So our r is going to be positive square root of y. Okay, any questions so far on the information we have? Yes, Mike?
So how do you know if it's gonna have a hole in the middle or not?
That's a really good question, and the answer is that we've got to draw the picture. So if, say, we had a curve here and then another curve that maybe came up on the inside, when you slice and you see that your slice is missing a portion here that we're cutting away, so it's a matter of understanding the region and then imagining the picture that goes along with it.
So is it just that the line's going through that one? Is that what it is?
Wait, say that last part
Is
again?
it that the line's going through that one? Like on the top end you get the X? value axis going through value one.
So I think what, maybe a good way to think about it is, if,
Which way it's rotating?
that's gonna be important too. If you look at this one, when you rotate about the x-axis, what you notice is that the actual curves don't touch the x-axis, so there's gonna be gaps in your picture. And so that's where you're gonna end up with a washer. Whereas in this direction, the region actually touches your axis of rotation, and so you won't have any gaps on that one. So I think that's what's gonna tell you. Yes?
If we were solving this for the equation, but if it was in quadrant 2,
Yes.
basically the negative on the x squared would cancel out the negative on the square root of y, correct?
And on this particular example, you're right, it won't make any difference. Some examples it may change your values, and so you do want to focus on which was the original region that you have and use that for your curve. Okay. Other questions? These are all good, really good questions. Okay, so let's continue on with this one. So the volume of one disk is going to be pi times r squared, so that's root y, quantity squared, times the thickness, which is dy. And so now our total volume is going to be pi times square root of y, quantity squared, dy, added up, starting, now here's something I need to be careful of. Okay. Because our thickness was y, and our radius was in terms of y, our boundaries must be y values. And so when I'm thinking about slicing, my smallest y value is down here at y equals 0, and I slice, 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 until I hit the top, which occurred at y equals 4. So our integral will go from 0 to 4. Okay, so now to answer your question here, we've set up the integral. Now we want to know, do we get the same volume as 128 over 5 pi? It's not looking good.
I don't know if this is, but it's just the reason why it was 2 on the x, because it rotated on the x, so you had to switch in the y for the x, right?
That's right. So when we sliced perpendicular to the x-axis, the x values went from 0 to 2. But we're slicing with respect to the y-axis, so our y values are going from 0 all the way up to the 4, which was our top line up here. All right, so there's our setup. Let's go ahead and solve this total volume. Our total volume is going to be the integral from 0 to 4. We can pull that pi out in front. Square the square root gives us y dy. Super easy integral to integrate. We get 1/2 y squared, evaluated between 0 and 4. We still have a pi out in front. And so we'll plug in 4, and so we've got 16 over 2, minus plugging in 0, and so we end up with a value of 8 pi cubic units, which is way different than 128 over 5 pi cubic units. So the moral of this story is that even if you start with the same region, the same area, depending on which direction you rotate it or what axis you rotate around is absolutely going to change the volume of your final solid.
I mean, it changes everything. It changes the parameters, it changes...
That's right, it's changing the parameters, it's changing the shape, it's changing the volume as well. All right, any questions about that? Going once? Okay. All right, so I think that maybe now is a good resting spot for these examples.